All right, so we're going to look at semi-homework question number 26. This is Hess's law. And I said in class on Thursday that you didn't need to worry about Hess's law. I'm going to go ahead and throw this in here since I did say that I would do question number 26. But this is not on the review quiz that you're going to see next week. So don't panic if you're like, I have no idea what she's talking about. This is something that we'll come back to and spend a lot of time with in a couple units. So again, no panics if you're like, what is happening? But if you want to preview, here we go. So the point of Hess's law is for us to figure out energy changes that happen in chemical reactions that we either can't measure because we can't contain them or don't actually happen for real, and so they are more hypothetical. We're given a couple reactions that do happen, and these reactions, we were able to measure temperature changes. We use those temperature changes to find energy. So delta H is the energy that is released during or gained, energy released or gained during chemical reactions. So this delta H, or change in enthalpy, of a negative 221 kilojoules means that 221 kilojoules of energy was released. That's what the negative tells us. Energy was released when this chemical reaction occurred. And this guy, 483.6 kilojoules was released. Again, that negative means energy is released when this chemical reaction occurs. So this chemical reaction, for whatever reason, we can't measure temperature changes during the reaction, and so we can't do our calculations to figure out our delta H. But what we can do is some amazing algebra. And so we're going to basically solve a system of equations given these two that we know to solve for this guy instead. So here's how it's going to work. We're going to rearrange those to make it look like that. I see here 2 carbons, and here I only see 1 carbon. 2, 1. Close, but not the same. So what I'm going to do is take this first equation, I'm going to chop it in half so that my 2 carbons goes down to 1 carbon. So again, I'm going to take 2 carbons and an oxygen, which makes 2 carbon monoxide molecules. I'm going to chop the whole thing in half. That's going to give me 1/2 times 2 is a carbon, just 1. 1/2 times a half, 1/2 times 1, invisible 1 is right there, is half an oxygen gas molecule, and that's going to give us 1/2 times 2 is 1 carbon monoxide molecule. You can draw your 1s or you can leave them invisible. All is good. So if I'm chopping everything in half, I'm also going to have to chop in half that delta H. So the delta H used to be 221 kilojoules of energy released, but now I only have half of that equation. I'm going to have to chop that in half. And so our new delta H is going to be -1. 10.5 kilojoules of energy released, which makes sense because if only half the quantity of the reaction is reacting, we should have half the amount of energy released. Good. Let's look at the next piece because I've got carbons and carbon monoxides, but I need some waters and some hydrogens. I'm going to get those from this second equation. So what I'm going to have to do with this guy, clearly we're going to have to chop in half again because I only have 1 water and I've got 2. I want 1, I have 2. We're going to chop it in half. But also, we're going to have to reverse the whole thing, flip the direction, because in this one, I have water in the products, and over here, I have water in the reactants. Products, reactants, not the same. So we're just going to take this arrow and flip it the other way. So I've got 2 waters yielding 2 hydrogen gases and 1 oxygen, but of course we're going to chop that in half. 1/2 times 2 is 1 H2O. 1/2 times 2 is 1 H2. 1/2 times 1, invisible 1, O2, is half an oxygen gas. But my delta H, what are we going to do? Well, we have to chop it in half because I halved all of that. We're going to have to take half of this also. But I switched the direction of the whole reaction. When you change the direction of the reaction, reverse that reaction, you have to flip the sign of your delta H. So instead of going this way, -483.6, going this way is going to be a +483.6. Positive 3.6, but now I have to chop it in half. Half of 483.6 is a positive 241.8. So again, just in case you're like, where did that number even come from? We took negative 483.6, we made it positive because we reversed the reaction. And then we took 483.6 and we chopped it in half because I needed only one water, not two. Good. All right. So now I'm going to take these two equations and we're going to add them together. I have one carbon and half an oxygen and one water in all my reactants. And then on the other side of the yield sign, we have one carbon monoxide, one hydrogen gas, and half an oxygen. Interestingly, half an oxygen here, half an oxygen there. Subtract half an oxygen from both sides. Gone, gone. So what do I have left? A carbon, a water, a carbon monoxide, and a hydrogen gas molecule. We did it. This equation matches this equation. How did I get it? I added those two guys together. So what do I do with my delta H? I add them together. Negative 110.5 plus positive 241.8 leaves us with 131.3 kilojoules. It's positive, which means that energy is being absorbed during this chemical reaction. Voila, Hess's law.